All right, thanks everybody for joining today's HPC Best Practices webinar. I am David Bernholt from Oak Ridge National Laboratory. I'll be hosting today. First of all, I do want to apologize for folks who joined last week. As most of you will know, we had to reschedule this webinar. This is only the second time this has happened in 89 webinars so far, and apparently the word didn't get out far enough. So to those who joined the call last week, I apologize. I hope you're back today or will be able to view the recording of this later. We do want to make this webinar as interactive as possible. And in order to keep track of things, we ask you to put your questions in a Google Doc. I will put the address in the chat, but it's also a simple link right here. And that way we'll have Antigoni try to answer the questions also in writing after the webinar, and we'll have that as part of the archive for the webinar as well. But we'll also try to ask the questions as you put them into the chat as we go through the webinar. The other thing I'd like to mention is that we'd really appreciate your feedback on all of these webinars, any that you've attended, and there's a link here with a very simple couple-minute form to give us some feedback. We'd appreciate if you could take a couple minutes of your time to do that as well. So I will now introduce Antigoni Georgiadou from Oak Ridge National Laboratory, who will be speaking today on high-performance computing and software sustainability toward green software development. Thank you.
Thank you, David. Yeah, you stop sharing, I can share my screen. Full screen, perfect. You down here. This is moving. Okay. Thank you so much, David, for the invitation. I think I was self-invited to some level, but this presentation today is under the umbrella of the Better Scientific Software Fellowship Program. And for that, I would like to thank Elsa Konchorowski and from Lannel and Eric Palmer from NERSC, who have been the organizers for that fellowship and that pointed me to this webinar series and gave me the opportunity to present my work. Today, I will talk about high-performance computing and software sustainability, and trying to ignite the discussion toward green software development. I am a scientist at the Oak Ridge National Laboratory. I'm part of the OLCF facility. So I'm a scientist in a leadership computing facility. And the discussion on green software and best software practices has been arising more often. Discussing green software in the context of scientific applications, which is part of what I do, is very important. Talking about how we can have scientific applications that are robust and create efficient software with respect to energy efficiency. Software will not consume energy by itself, but can indirectly influence operations within computational resources, and that can contribute to activating cost in energy, carbon emissions, etc. On the hardware side, software like hardware on the software side is part of the problem for the environmental sustainability, and the discussion about best software practices will be one of the aspects to be considered for future planning, and when we're talking about HPC and the post-exascale status of HPC. And within this framework, today I will discuss my current future work and try to enable a somewhat a discussion on a somewhat green software philosophy. And talking about green software, green has many shades, 50 shades of green, but where we will be talking about the trade-off between how green we can go on our best practices without compromising science. So it's green software for science. A little bit about me. I'm Antigoni Georgiadou. I'm a mathematician by training. I'm staff here at our National Laboratory, and I'm part of the Algorithms Performance Analysis Group. Phil Roth is my group lead. I've been part of astrophysics collaborations and part of the liaison for different projects and teams that run on our systems. I'm part of the hack team, the cosmology simulation team, and the HPC fusion code. I'm also a member of the technical committee of INSITS for Fortran. This is the committee that works on interpretations of the current standard for Fortran, and it develops the list of new features. So this is led by my colleague here, Ruben Gutierrez. I'm part of the ADAC Institute. I'm the executive committee there, and I am the chair of the workshop that was part of the supercomputing conference for 2 years on optimization and uncertainty quantification on HPC. This is part of my background with respect to the computation and outreach aspect of the discussion today. I had the honor to be an honorable mention of the BSW Fellowship for the year 2024, and this on the right side are my amazing cohortees. This is a nice group of people that I met, and we presented our vision with respect to the BSW Fellowship. I learned about the BSW Fellowship through the ECP program that I was part of, and I decided to write a proposal with respect to the ongoing discussions that have been going on my facility and the general scientific community. And I was aiming with my proposal to do an activity to raise awareness on good software practices, how to improve scientific productivity with respect to that, and inform and have interaction on efforts for sustainability planning. In that sense, I propose to create YouTube videos with a podcast style or seminar style, which is ongoing and under planning. In the meantime, this year, I was part of 2 papers, one on energy efficient visualization of large-scale data that was a part of the ASCR energy efficiency workshop that was led by my colleague here at Oak Ridge National Laboratory, Tushar Athawali, and another paper that was part of the supercomputing conference that was about towards sustainable supercomputing for the post-exascale era, led by my colleague here, Woon Shin, at the Oak Ridge National Laboratory. I will talk about briefly these 2 papers later in my talk. And under this fellowship, I aspire to have these videos and produce this media to build community, have open conversations, discuss and interact to get feedback from different parts of the community that this topic concerns, contribute to training and incremental improvement of best practices. And the vision is having the opportunity to discuss supporting and sustaining software and overall outreach to the community for that. I would like to reach out to the people attending, keeping in mind that this is not a funded project, that it would be great if you have any suggestions about support for audio and optical recording infrastructure, and also besides the list that I already have for the speakers that I will invite, I would like to see who, if you have someone in mind, you can volunteer, or you can volunteer yourselves if you think that this is a topic that is of interest to you and you're familiar with it. My institution has been very sensitive to and working towards energy efficiency. It is very critical for Oak Ridge National Laboratory, and the discussion is ongoing in several levels. If you go into the highlights and media that have been worked on and produced from ORNL, you will see many different aspects of energy efficiency and sustainability across research areas and touching different parts of society. One of them that I found very interesting is the one that the researchers turn coal into graphite for clean energy, meaning that they take some component that is definitely bad for the environment, and like alchemists, they contribute to make it being useful and take this otherwise unwanted material and make it into something that is useful. So in that sense, this discussion for energy efficiency on supercomputing is very current, very relevant, and it touches the mission of the lab. On the supercomputing side, supercomputers and energy go hand by hand, and greenness, if I can use this word, is a constraint that should be optimized to enhance power measurement methodology. A typical supercomputer, like Frontier that we have downstairs here, will consume electrical energy that could be used by a small community, a small town, and that energy is converted to heat that requires cooling to be processed, and this is how we deal with all this energy consumption and the output of it. Ranking and looking at the energy consumption of supercomputers is really important in my community, and it's being done through two rankings: the top 500, which gives the performance across supercomputers across the globe, and the green 500. Our systems have scored the top rank across rankings, and the Frontier has ranked number 1 in the top 500 list for multiple years, and its TDS system reached number 2 on the green 500 list the same year. This ranking occurs twice a year and has a power measurement methodology. It has metrics that in supercomputing we use flops per watt, and it uses tests the high performance LIMPAC HPL, and it takes levels of power measurements, which is the range from average power to energy consumption. It uses Rmax, the maximal LIMPAC performance achieved, and Rpeak, theoretical peak performance, to make the calculations and ranking for the supercomputers. On the software side, this discussion starts from AI and how expensive it is. I think power consumption in the data centers and HPC centers like ours here in OLCF is gradually becoming a hot topic, and there is a universal effort towards green software development, both software and hardware, and this touches across fields, academia, government, and industry. And this discussion started on how to produce better software in terms of more energy efficient approaches. But what makes software cost efficient? In general, in literature you can find best practices you can take. It usually is hardware specific, and it's also application specific. But in a more general, high level, you can achieve desired science results while minimizing time to execution for given tools and architectures. So there's always a trade-off. You have to go green, you have to be cost efficient, but still you have to make sure that you have the desired science results. And this usually translates to minimize time to execution. We have tools and architectures right now at our hands, but probably there's a discussion on how to optimize that. And for codes themselves, there are ways that we have to think as a community of optimizing modular design, go into more of open source technologies that are well tested and widely used. So that means that they give the better outcome, and the code optimization is achieved there. Automation can contribute to that, figuring out what constraints, what parts of the codes on an application are repetitive, or they are redundant, or they should be optimized with concern to the hardware they're using. Continuous integration also for automated build, testing, feedback loops to eliminate blind spots. On the data side, I've been part of this paper. It's a position paper. It's a white paper. It's a position paper that we did with, you see the authors, my co-authors here. It was led by a scientist here at Oak Ridge, Tushar Athawali. He's in Dave Bagmar's group, and it was on uncertainty-informed approximate computing for energy-efficient visualization of large data. So this workshop was driven by Asker, and it encouraged the submission of position papers to tackle current and future challenges and threats for energy efficiency. This was one of the papers that were accepted. A little bit more about this paper and this challenge with cost-effective visualization of large-scale data, how to do that. So the main idea is that you can use uncertainty visualization as a mechanism to achieve maximal energy efficiency and accuracy. So if you see here on the right-hand side, my favorite application, Supernova, that's not my result, but they're using it. You have original visualization, and you go in and you have reduced data with spatial uncertainty visualization in red. So so in that sense, when you look at your data and you visualize them, you can use greater precision in the regions of interest that have high uncertainty. So this is the way that you can have a trade-off between how much data you can use for your studies. Visualization is part of every science, and an impact of this opportunity to be pursued is an uncertainty-informed visualization that helps scientists that can reliably analyze data, large data, with minimal energy consumption. So you drop the visualization accuracy, and then you get energy efficiency. The challenge that we have, and it's not yet understood, is what's the trade-off between energy and precision that you keep. So when you go and try to optimize the data that you keep and handle by using approximations like, for example, low precision, dimensionality reduction, interpolation, what effect does that have on the uncertainty in energy? This is something that is not has not yet been studied, and this is an opportunity that comes in when we're thinking in these terms. So in this paper, Tushar and the rest of the authors, we suggested that two-therads, how large data can be best approximated while capturing uncertainty, and how uncertainty can be leveraged for energy efficiency. And some barriers that we are revealing is that developing energy efficient uncertainty visualization algorithms will need rigorous statistical derivations and visual mappings. So you will need the visual tools and a way to actually capture and interpret these studies. On that note, there were a lot of questions and a lot of questions to ourselves. What do we propose to do with minimal jargon, and why should we do that now? We should do that now because large-scale data and energy efficiency has become more pressing to acknowledge and take action on. And what difference will it make a breakthrough? We think that it will. How will we know we're on the right track, measure success? So we need some metrics, and should we be able to understand the way we are looking at this is the correct way? And this study should cover all the work that is being done today and what are the roadblocks, and why, and understand why overcoming these challenges is difficult. Define also the key steps along the way, so you need a timeline, and thinking about how this research and development unfolding will be done the next decade or so. The barriers and what resources you need. You need test beds, you need infrastructure that will enable visualization, etc. So it was a nice paper that gave a nice map of what we need to think about when we talk about visualization and large data. On the supercomputing side and on the side of the Leaders Computing Facility that I'm part of, we have been discussing and preparing this paper for a C on energy efficiency for the post-exascale era. And the aim is to reduce the environmental impact. And that translated to us, I think, that was my take on this, that supercomputing means power efficient for the most powerful chip. So you still need the power, you still need the best science, but being power efficient. And energy consumption, thinking that energy consumption might bound research projects and topics, and by optimizing the energy consumption, we might enable science for otherwise restricted practices. So making room, making way for other scientific applications that might need to use our systems. With this discussion, we're aiming to find solutions, best practices to save money over the lifetime of a computing system like ours. Our systems live for 4, 5, 6 years. And the solutions that have been given are on application and device agnostic tools, although we might think of application-specific tools, but in my opinion, yeah, it should cover any system that comes our way, any hardware device, and simultaneous software and applications and application optimization for energy efficiency. So this is a paper led by my colleague here at OLCF, Wong Xing, and it was many of the people in OLCF, my colleagues in OLCF were part of this. This has been an amalgam of the contribution of different parts of the OLCF house. From my section, which is the science engagement section, we have the applications, we do the science, HPC, operations and technology integration. And this paper was presented at the C24. It has been covering, this paper covered the strategy to optimize for energy efficiency for specialized hardware in targeted applications for sustainable computing growth. So we're looking at the HPC viability and how energy efficiency best practices and solving and giving answers to this challenge will make HPC post-exascale reliable. On the side of the paper covers the hardware side, we work with the software developers, with hardware developers to enhance the understanding of green practices. On the software side, the paper discusses targets utilizing the maximum of the resources provided for optimal science per watt result. So we're always looking at how much science we can get per watt. This paper discusses policies that ensure multi-tenancy, for example, in the future for unused resources. So you get more science in the idle places of the nodes on a supercomputer, and also workflow tools and data management. And in that sense, the discussion was on how green we can go. Is there a conditional stoppage that would make the practice non-robust? We cannot go further. What shade of green we have to stop? And I think the answer, the criterion is the moment you start compromising science, and then there will be no point of continuing to optimize. I suggest you go and look at this paper. It showcases different parts of what a leadership computing facility does and how it can be optimized, maybe embracing control and orchestration complexity under energy-aware policies. So it's it covers nicely this discussion, and going into more into scientific application sustainability, maybe mixing computing technologies in a supercomputer to achieve lower cost and best power per scientific output. This paper aims on taking the best optimized usage of the computing resources and giving the best science per watt, and optimize and save money over the lifetime of a computing system. It's just a review. So for sustainable HPC growth, we would like to see wider covered solutions, a higher level discussion. I think the usage of the better usage of GPU accelerators across applications. We should see the history of GPU usage on different applications, optimizing that and looking at how CPU versus GPU usage can be optimized on different applications. On the operation side, the responsible utilization of resources in the sense that you don't waste parts of the resources you're using, and always considering the trade-offs and effort to develop policies for accurate science with cost-efficient HPC. Back to, I mentioned AI, and this is, I think, spurs the discussion of why we need energy efficiency. I'm attaching here a plot from a paper we published with Wayne Joubert, Philorov, Bronson-Messer, and others on AI for science on a leadership supercomputer. These are results of the usage of AI on Summit, and how people who use our systems under different allocations propose and report on using HPC. So this plot is a heat map of the AI motif, what classification, for example, analysis, fault detection, etc. And this is a heat map that showcases which domain, which discipline proposes to do AI on a supercomputer as part of a subgrid model or some other method when they're using a supercomputing facility. We see a standardized increasing demand and use cases in AI machine learning. And these are a driving factor to changing the footing on energy consumption practices. AI seems to be not efficient. It has intense usage of energy and higher rates of data movement, and there is a catastrophology on AI's energy consumption, can contribute to climate change, can strain electricity grids, increase the demand for water for cooling when we are talking about data and HPC centers. And this is some media coverage of AI and energy footprint. Hopefully, if you're interested in that and we share the slides, you can go in and see my favorite articles and media for this discussion. But going back to the facility strategies, there are strategies to mitigate those efforts, retraining on better data, of course, model pruning, optimization to remove the redundant, source code enhancements, how you deploy them, modification to optimize the results, regularized to treat undercutting and overfitting. So in that sense, the culprit of this discussion, it's not the end of the world, and we have to think about and manage the outcome for the future of HPC. I will go in now and talk about an application that inside. This is our program, the Insight, one of the programs that we allocate our systems with, and the application that I will talk about now is part of, has been part and is part of the Insight program, and we have been looking at it for energy efficient purposes, energy efficiency purposes and studies. I include here, so I feel like I should include here my favorite media articles and everything that is on the topic. And I have here the YouTube video for Insight Proposal Writing webinar and some Insight articles. I will talk about HACK. HACK is the hardware hybrid accelerated cosmology code, and it's a cosmology code that this team from Argonne simulates the universe and computes large-scale structure of the universe at extreme scales. This team is using our systems, but HACK code is portable to any supercomputer in the world. So they're using many supercomputers. And for this study here, for this science, the aim is to enable the extraction of fundamental physics from upcoming cosmological surveys. So there are cosmological surveys that look up in the sky and they measure, take measurements of the structure of the universe in different eras. These studies, these observational studies should be matched with theoretical data, and because these cosmological observations, and these are one of the impossible experiments. They cannot be done in a laboratory on Earth. You are able to simulate that laboratory in a supercomputer. So you create a simulation that explores dark matter, the energy, understand and characterize systematic errors inside the observational studies. And the scientific challenge that we have and we face is with HACK is being done with a gravity-only simulation code. So this gravity-only simulation code has these big problems, many particles that simulate the structure of the universe, but also it has another component, the hydro simulation, that has a lot of physics. It describes star formation, galaxies, AGNs, gas formation. So you have groups, clusters, and a whole bunch of different scale of physics going on. So I will try to play here this. I'm wondering if it will play. I will want it to. If I. Oh, this is a PDF. Let me see. Oh. Maybe I'm not able to play this this video, but I will point you to I'll point you later in the slides to see this this simulation. This is the formation. This is the hack code was able to do the largest simulation being done so far. It's not only how big it is. It's also the quality, the parts of the physics that it includes. This is what you see here, a small part of the universe. And if I was able to run it, you will be able to see the evolution and formation. This is a cluster of galaxies, and you could see the formation of galaxies ranging from billions of years till now. So it's a nice, neat evolution simulation that describes the expansion of the universe. In that sense, you should be able to find this. This has made a lot of media traffic, and you should be able to find discussion on it, on articles that I include here. For example, PIs are discussing, make comments in that, and you see that this is a record-breaking run on Frontier, and I was the liaison on the OLCF side, helping them run on Frontier. On the hack side, hack has a lot of programming models that it uses so that it can run to many platforms. But for Frontier, we were able pretty straightforwardly to run it with HIP, and we were able to use up for our ECP goals 8,000 nodes of the system. Right now, for the simulations, we were able to use 9,000 nodes of the system, and I include here 2 papers that we co-authored. They were both at the supercomputing conference, and it's worth looking it up. It's not only the hack application; there are more applications there that you will see performing on Frontier. And in that sense, hack has this part of the code, the short range force that takes the whole, the most of the computational time. And looking at that, this is a Vlasov-Poisson, has a Vlasov-Poisson solver, and you should be able to optimize. So we're looking at it with energy performance tools, looking at the application and being able to, looking at it to be able to optimize it. These measurements for hack, we have all these the most interesting kernels, the kernels of interest that we're looking at. It's a fast Fourier transform kernel. These are the MP kernels, and we're looking at it. We ran it for 1,000 nodes. This is the gravity only code, and we see we're trying to understand the behavior. And this spike right here, or looking at it, we think that it's something that we can turn off. We don't need that the development over there. So it pretty much takes a step, drops down, takes a step, drops down. So it's a sustainable behavior we're trying to understand and optimize. This work is led on the application side by my colleague Trey White, and we have been looking at the different profiling assessment and tools. We looked at the SACCT command that you can run. You can use it to extract the consumed energy, the raw consumed energy, and you can look at it. You can use it actually when the job is running, but also you can do that really right after the run. It can take accounting logs when it is in queue and if it's recently completed. And this is the example for the one node run. So for the good thing for the hack code is that we can scale up the whole machine, and this is a perfect application to look at. Another, so we have a postdoc here at Cornell, Matthias Meitert, and he has been looking with different tools for one node run using CRAMP to look at the GPU memory usage and overall usage of a hack. This is these are stacked data, and these spikes are being noticed here. We're looking at them, and we think that turning off the load balancer it will help removing those spikes. Although taking more sparse data and launching a profiling tool right before a significant event that we know it will happen, like taking a step, it will help with better optimizing the performance and the energy consumption assessment. Another aspect that we're looking at is the mixed precision support in HPC applications. This is a paper that I got interested in, we got interested in, and it looks at different applications that and the precision usage they historically, typically, and is being used across domains. So this paper, I reference it here. It showcases different scientific domains. These are benchmarking codes, different disciplines, and typically, historically, how they use the precision when they run on an HPC system. Single precision support, mixed precision support, double precision support. And the idea is how, and the paper here is looking at weather modeling, is at the forefront of mixed precision, for example, and use single and mixed precision leads to fails. This is how they are looking at it in the paper, but trying to challenge the usage of precision on different codes, and trying to see how we can get accuracy with optimized for precision, bringing them a little bit up and trying to challenge that probably will be the next step to acquire better energy efficiency. In that sense, uncertainty quantification can play a major role to that. We can go with the guess and check methods, go in and do trial and error based on expert knowledge, or we can make it more of an automated, make it in a more automated way. And in my opinion, uncertainty quantification for this challenge will play a role in that and should contribute to that. And in my opinion, it will contribute to deciding mixed precision and other decision-making aspects on the optimization of the software being done, being optimized for energy efficiency. With respect to supercomputing, we have hard problems to solve, but always it's the solution per watt, the theoretical result per watt, and how you can handle the data intensive computing. In my opinion, uncertainty quantification will play a role into making these decisions. I will take this time, if I have time, David, to advertise our allocation programs. One of them, this is an old slide I'm using in my presentations. We have Frontier. We allocate Frontier through 3 allocation programs: the Insight, ALCC, and DD. The leadership computing for problems that require leadership computing and require a big part of the machine, or they have data needs that cannot be met anywhere else. You should look up the Insight submission process. It should be open this spring till summer, and if you really need these computational resources and computational power, there's no substitute for that. So I'm the liaison for different projects, so come ask me. I'm or one of my colleagues at the science engagement section on how to prepare and submit a successful proposal to get allocation hours through the Insight or DD or ALCC program. On that note, I will share my slides. I have included here my favorite references on the topic. And with that, let the discussion begin.
Thanks very much, Antigoni.
You're welcome.
So we've had a number of questions come in, and I will go through what we have in the Google Doc, and then we can open it up for further discussion with the group after we get through as many of these as we can. So the first question is, have you had any experience with the Green Algorithms project? And they provided a link in case you're not familiar with it. You can get estimates of your HPC carbon footprint. And I wonder if just putting it in understandable terms, i.e. It reports car kilometer equivalents, could motivate researchers to use compute resources more responsibly, or is the main limitation that they lack the knowledge of how to do more efficient computing?
For the first part, I think of the question is that I'm not familiar with that, but thanks for sharing. I think it's one thing that we can bring up more. I will look it up. The second part, I think it's both, and scientists and the scientific community would like to do the best science. So they don't want to compromise in their science results. So that's why they go in and they use, for example, double precision, and the thought of optimizing it doesn't come really easily. There's no need right now. Till now, there was no need to do that. And with policies enforced, I think that the large HPC clusters, given accessibility to these codes, or the discussion of enforcing policies and supporting codes to be run on leadership computing facilities that are more energy efficient, and they have been optimized towards that, I think they will be coming more and more. So this is not enforced right now from any facilities that they let their users run, but it will come up, and it will be a criterion of who's running on a large HPC cluster.
All right, thanks. Another question is, nuclear reactors are green. The top few HPC machines on the top 500 list have 20 to 30 megawatt power ratings. A nuclear powered aircraft carrier is run by a reactor of about 700 megawatts. A small nuclear reactor alongside an HPC machine is green. Why does the speaker not mention nuclear reactors as a green solution?
Yes, yes, and if you see, yeah, that's something that should be added for sure. I'm pretty sure it's part of the discussion, and reactors, fusion reactors, or reactors that can support this are in order. You hear from industry like NVIDIA that their new data center will be supported and be supported with energy from a reactor. So I think it's you're right, it's a big part of the discussion and should be mentioned. It wasn't covered.
I'll just interject something here from my own knowledge and experience, which is that it's not necessarily only about being more green in the climate-friendly sustainability kind of sense, but it also has direct implications for the cost of running the system. Power costs money no matter where you get it from. And if we're running a system, so we use a rule of thumb here at Oak Ridge of a cost of about $1 million per megawatt hour per year. And so that means a 30 megawatt system is going to cost $30 million a year just for the power bill. And if we can get that down, if we can run the system more efficiently, then we can excuse me, then we can lower our operating costs. And so that's also a factor in, why we've gone with GPUs. They have a lot better compute per watt than standard CPUs do, for example, and this is kind of an important trend that's been going along in the whole HPC community for a while now. But that editorial out of the way, I'll go on with the questions. Should we be discouraging users from using inefficient codes written in Python or R, or are those insignificant blips in the grand scheme of exascale?
Python is it's been used in our facility in an increased rate, and I think it's a big part of AI. That optimization should not should not be the mainstream. So this practice it has come to stay, and obviously using Fortran or C++ should be more efficient. But discouraging them, but will not solve the problem. It's more of on the how you use it, how you optimize it, and for best practices on how to set up your problem and how to optimize the data you're using for AI, when we're talking for AI.
All right, another question. Can you elaborate on the tools you're using for energy efficiency calculations? What languages does it support? Is it architecture dependent? How are they calibrated?
Yeah, so the tools that we have in mind are architecture specific in that sense. And so that's why we have in mind and thinking and having the discussion of taking tools that are architecture agnostic. We are using, right now we have Frontier is AMD and HPE, and we're using tools like I showed you today the AST command tool that takes the raw consumed power, but we're using CRayPad. And also another tool that we have in mind is the Omnistat. So, and another tool that our colleague here is using is the CrayMP. These tools are, for example, that the last one is taking it's the Linux interface. It takes the data, raw data, so it takes a lot of cleaning of the data so that you can stack them together and make a sense out of the results. So in that sense, there's a discussion of what tools should we build so that whatever system comes after Frontier has these tools and can utilize them. In my opinion, they should be application agnostic and architecture agnostic, but this is a level of another level of optimization. So for now, our tools are architecture specific, and we're looking at applications on which tools can be better used. So I would say that also they are application constrained.
All right. In one of the slides, you mentioned numbers for the consumed energy coming from what looked like a Slurm job. What are the units of those numbers?
I think these ones, I know which one you're mentioning. I think I included that. These are joules. And this is the SACCT command that we're running for a job on Frontier.
Mm-hmm. Is it recommended to use full precision?
Full precision, no precision is recommended, but its scientific team would like to get the best results for their science. So I think they're trying to use the most of the precision they can get. I think what the discussion will be in the future is that the recommended precision usage should be optimized, and every application should look at how better they can lower their precision they're using when they're launching a job on a supercomputing facility, so that they have the better energy efficient run with with the result of the science that you would expect normally.
Okay. How much electricity can we expect to save by writing more efficient codes?
I would say that optimizing the software, we will be able to optimize the usage of the computing resources. So I don't have a number in my head, but the way I'm seeing it is schematically looking at the resources and making the best out of them, and not only using less, consuming less energy, but also allowing for other science to take place in otherwise excessively used resources. So I think it's a win-win when you bring down the energy cost, but also allowing for more science and different science to be done on a supercomputing facility.
Okay. I was really hoping to see some actual example code with before and after being green, more green. Do you know of any resources for this kind of thing?
Yes, yes. So I think here I have some. So I include examples, but I would like to point you to the last bullet right here. It's work being done by a visitor that we have here at the OLCF these days. He's a professor from Brazil. He has been looking at the thread usage for CPU and GPU. So this is one example that I can point you to.
Okay. At the outset, it was mentioned that electrical energy is used for the calculations. This turns into heat, and then energy is used to remove the heat. Are you aware of any projects that repurpose the heat rather than remove it? For instance, in cool climates, heat energy can be captured, say, by a thermal battery in the ground or used to heat buildings during cold months.
Yeah, yeah. There are different ways of taking that heat and transmuting it to something more useful. In my opinion, here so we have this cooling process that we take this heat and we make that we cool it down. So that's I think the future of HPC and how cooling will be done. But yeah, of course, thinking of how to give back to the society with transmuting this energy to heat the small cities that are near a facility, that's a way to go. But I don't know any other. I cannot think right now of any other ways of using this this outgoing energy.
And the last question that we have, Dr. James Demel of LAPAC fame conducts research related to communication avoiding algorithms, thus more energy efficient algorithms at UC Berkeley. Would it be useful to contact his group regarding HPC sustainable software, or have you already been in contact with them?
No, and thank you so much for conveying this information. Yes, and with that, I would like to say that please feel free to reach out to me. with suggestions like this one, the last one, and in the near future, the next 3-4 months, we'll be having these discussions being recorded and given back as outreach and as video. So yes, please let me know if you have any more suggestions like this for me, for groups that do this work and for speakers that would like to enter this kind of discussion.
Well, thank you very much. That's all the questions we have, and we are also out of time. So I want to thank everybody who participated today. We will be, of course, sharing the recording of this and Antigoni's answers for the Q&A once we get them, hopefully in about a week. And please feel free to share with friends and colleagues. And of course, contact Antigoni if you want to follow up on some of the things she's talking about. Thank you very much.